In our coming study of amplitude modulation and in understanding a sample and hold system, it's useful to have a device, a linear device, called an operational transconductance amplifier. It's an op-amp whose gain is adjustable. So recall our model of the op-amp. We have an op-amp, and we have it as a model where we have an input port with a very large input resistance between them, and that voltage difference controls the voltage of the output. And in the ideal case, A is very large, R in is very large, and R out is very small. So differential input changes the gain, which leads to the output. For the operational transconductance amplifier, OTA for short, we have a very similar model. It's still a differential input, but the voltage-controlled voltage source is replaced with a voltage-controlled current source. And we control the transconductance of that source, the gain, how the current out relates to the voltage in, with another current that we put in, the amplitude bias current, which I show coming in here and going to ground. That's not exactly what happens, but it comes in and goes to ground, and that current controls the GM value. The other difference is that R out is not small. It varies depending on the gain, but it's a large value of resistance. So in this class, we'll use the 3080 OTA, and we can understand it using a pair of current sources, or a bunch of current sources and a differential pair. The current sources here are all basically current mirrors. We have current mirrors like this that we saw in class, and since this transistor is diode connected, we can actually sometimes replace it with a diode picture like this, though this really means that. In the schematics for the 3080, you see this show up a lot. And I'm further going to make this into a component where we have the input I coming in here, and it controls the current flowing across this way. So in the OTA, the IABC controls the gain of the current source, and that's here. So there's a current source here. Remember, that's going to draw a fixed amount of current, and IABC controls what that current is. In the current mirror case, that just is the whole current. And so the differential pair, right, so here's the inputs to the differential pair. Normally we would change the voltage through a resistor, but here we just want to have a slight difference in the currents based on the difference in the voltages. Those two currents come this way and that way, and the difference of those, if this one's bigger, it pulls more here than this one's putting out, so current comes in. The difference is taken here of those two currents, and that's the output current of the OTA. And so if this voltage is a little higher than that one, then this is a little bigger current. So this current is a little bigger than that one, and that has to come from here. If this voltage is a little bigger than that one, then this one is putting more than this one wants to take, and the output has to come here. So that's basically the way the 3080 works. And in particular, there's a few constants for the 3080. The gain, the current gain, is 19.2 times the current coming in milliamps, and that will give a gain in a micromho. So you can control the current that comes out based on the voltage comes in with this. That's 1 over resistance. It's a conductance, and that's why we measure it in mho. The output resistance, you see, is 7.5 mega ohms divided by IABC, again measured in milliamps. So the output is linear for currents from half a microamp to half a milliamp. That's over 60 decibels, so it's a big linear range. And one needs to control the IABC by knowing that the voltage of its port is one diode drop above minus VCC, or the the negative power of the circuit. So you can see that in the picture here. Minus VCC is here, IABC comes in. There's clearly a transistor in here, and we have a diode drop coming down. It's actually this diode. So that's all there is to say about the OTA until we start to use it.